let's go ahead and start again. So this one, all good. Okay, so the second talk is more about choice models. And these are more research topics that I conduct with my team, but they're not really sponsored. So these are not really funded projects. These are activities that I kind of participate in because I love exploring these questions. These are choice models that you may be familiar with discrete choice models. With a show of hands, how many of you have studied choice models? Yep, there's good numbers here. So, yep. So this is basically one of my kind of favorite topics, and I develop choice models without using existing softwares because worked with softwares a lot, but softwares do have a little bit of limitation in terms of the type of choice, especially if you want to use dynamic discrete choice modeling, then there's no softwares out there that you can use. So I'm presenting on two research topics and two papers basically that are dealing with choice models that we developed on our own without using existing softwares. So this is basically dealing with dynamic discrete choice models and particularly dealing with recursive logit. So the content doesn't seem to, okay. So the contents of this presentation basically start with some backgrounds of importance of sustainability and research in travel behavior to support sustainable growth and sustainable transport and pathways to mobility as a service. And then I'll talk about two models that would support decision-making in this space. The first model is for mode choice modeling, and the second model is for path choice modeling. So let's start with a little bit of background, talking about emissions, especially emission in Australia. So a philosophical question. How much emissions are we allowed to produce in transport? How can we answer that question? How much, for example, CO2 are we allowed to produce in transport? How can we tackle that question? Any thoughts on this? So you can actually look at this question from two perspectives. First perspective is in terms of absolute values. So if we look at, for example, trends of global warming, and particularly, for example, if we consider Paris Agreement. Paris Agreement was among many major industrial kind of countries, developed countries, and the agreement was basically dealing with emission in a way that it keeps global warming to a maximum of 1.5 degrees Celsius. So one way of looking at how much are we allowed to produce emission, especially in transport, is to look at absolute terms and absolute values. Are we doing well considering Paris Agreement? Are we along those lines to reduce our emissions contributing to global warming below 1.5 degrees Celsius or not? The other way of looking at this is in a relative term. How are we doing in comparison with the rest of the countries in terms of per capita? It's reasonable to assume that once you meet, for example, the absolute terms, you would also want to make sure that you're not outstanding and you're not producing more emission than the rest of the world population. And on both of these levels, I mean, Paris Agreement, Australian government is coming out of because we may not be able to achieve those targets. And in terms of comparing with the rest of the world, we are not doing well. For example, in a recent kind of economic analysis, comparison between 23 countries that produce majority of the emission in the world, Australia ranks almost second worst in terms of per capita. Our population is only 24 million. And the amount of emission that we're producing, about a third of it comes from transport, and almost half of it is dealing with passenger cars. We have very spread out cities that would require a lot of driving, and we have long distances of travel. If we look at, for example, data from Household Travel Survey, a city like Melbourne, we have something about 10% only public transport use. I was in Seoul a few days ago, and I was really impressed with the public transport and how people really intensively and efficiently use public transport. We don't have such a thing and that attitude in Australia yet, but we should be moving in that direction. So I'm trying to address questions that are related to this and identify the main anchors that get us stuck to our cars and to the car culture. So part of it, so if we look at, for example, efficiency of transport, especially these are calculated particularly for Melbourne. So you can see when it comes to resources that we use, the first important measure of resource that we use in transport is our time. How much time do we spend to go from A to B? And the second measure is energy. How much do we, how much energy do we use and how much emissions do we produce? Space is also another shared resource. How much space do we take on the road to get from A to B? Cars, especially single occupancy cars, are known to be one of the most space-intensive modes of transport and the least efficient in terms of using space. And mass transit, on the other end, is usually the best mode from the space perspective. Remember the distance that we talked about that vehicles keep from vehicle in front of them? That's the issue with transport. For every passenger in a single occupancy car that drives a corridor, they need to keep a distance of like 20 meters with the vehicle in front of them. That doesn't happen in public transport on a train. You can actually sit next to the fellow passenger or stand next to them. So that's efficiency of space when using public transport. So from both energy efficiency and space efficiency, driving seems to be on the worst part. So it's important to be aware of this and do research and encourage more use of sustainable modes, especially walking and cycling, because these are not only sustainable, but also really good for our physical health as well. Any questions about this chart and about this content so far? Okay, so we understand passenger cars are easy to use if we can afford them. They're flexible. You have control over space. You have control over access. But as transport engineers and transport planners, can we produce an experience for people that is close to passenger car? Because if we can do that, we may influence their decision for more sustainable modes of transport. So you may have heard the term mobility as a service. So mobility as a service, as opposed to mobility that is owned. For example, when I buy a car, I buy my mobility option, and I use that when I go from A to B. Mobility as a service, on the other end, is when you basically outsource the mobility as a service to a third party. And if they can provide the flexibility, the speed, and control and access that you need, then it would actually be a more sustainable alternative. However, over the past 10, 15 years that the concept has been introduced, I do not know an example that has been a really good success in winning over the mobility market from ownership side. So I think there should be good amount of research questions in this direction. What gets people stuck to their cars, and why do people drive as much as they do? There are tons of research out there, but there are more opportunities to do good research. So mobility as a service can provide the speed, flexibility, and control without the externalities of personal traffic congestion. But it seems to be not as desirable. And in this particular paper, I'm trying to uncover some of these issues. So if we look at the reasons, personally, that I drive, for example, I drive in Melbourne, but I try to minimize my driving. For example, when I go to work, I don't really drive. I take public transport, but sometimes I have to drive. So let's look at the particular reasons in transport research from different dimensions. So there are social and behavioral sciences. There are some more advanced kind of research reasons, and there are classic transport planning reasons. So the first cluster of questions is basically, if I own a car, I will drive it because I've already paid for the lease, for the parking, for the insurance. I've already paid part of that kind of cost. So when I want to use my car to go from A to B, the marginal cost of operating it is going to be probably cheapest. So that's part of the reason. I probably have already made other decisions, like residential decisions, lifestyle decisions, where I live, where I work, where do I go to gym, where do I do my shopping. All of these decisions would basically interrelate with my decision to own a car and run a car. So understanding all those decisions, there is good body of research that deals with that. Social behavioral sciences mainly, transport planning, and transport science. There's another class of reasons. If I take my car out of garage, I will drive it. For example, if I take it in the morning, for the rest of the day, I probably go to every destination that I need to go using my car, and then I'll have to bring it back home with me. So part of this is that I cannot leave it out. I need to return the car back to the garage. And the other part is that if I need the car later in the day, for example, if I want to do shopping in the afternoon, or if I want to pick up my kid from the school in the afternoon, I should take the car with me in the morning to make that option available to me in the afternoon. So there are some hidden reasons. I may need my car later. Because I may need my car, I may take it in the morning and contribute to the congestion during the peak period, because in the afternoon I may need it. So I call these some of the hidden layers and hidden reasons of mode choices, especially for driving, that is not really addressed as much, because they're usually more complicated, at least in terms of choice modeling. The data doesn't really exist there. The last cluster is basically the classical models in mode choice and in transport planning. If I actually need to drive, I will drive. If there are places I need to go that are only accessible by driving, I may drive. If I need to do shopping, I will drive. If I need to give ride to others, pick up my kid from school or drop them off at the school, I will drive. So these are direct reasons that have accessibility kind of tags behind them. So there is good amount of research over the past 50 years. Actually, the first paper in discrete choice that Dan McFadden actually presented at his Nobel Speech Prize. He won the Nobel Prize for his model on discrete choice. And they tested the mode choice of BART system in San Francisco area. So his talk at the Nobel ceremony was dealing with an accessibility model for mode choice. And after that, over the past 40 years or so, he got the Nobel Prize in 2000, but it was for a paper that was written in 1970s. So over the past 50 years, majority of the models out there are dealing with accessibility reasons, not the hidden layers. And less so, I mean, not as much as accessibility ones are in behavioral dimension. So lifestyle decisions and residential decisions are studied in behavioral sciences. Accessibility reasons are studied in transport modeling and choice modeling. So my question is, can we predict the value of mass considering the chores of individuals, like considering the entire selection of trips that people need to make and considerations that may have throughout the day? Because if I can provide mobility as service, for example, when they need, if I can promise the population in the city, if they take public transport, in the afternoon there will be a taxi to the price that is affordable to them to do that particular single trip that they have to have a car with them. Or there will be like a bicycle, an electric bicycle available to them for a particular trip that may need a bicycle. So the question here is that, can we quantify the value of mobility as a service, the value of an alternative that would be available to them exactly when you need it, and then understand its effect on mode choices and its effect on helping people leave the car at home or not buy a car at the first place. So the objective here in this particular paper was to model tour-based mode choices and quantify individuals' forward-looking behavior. Examples are given here, and I talked about those. If I walk to work, I will forego access to my car for the rest of the trips during the day. Or if I take my bike to a social event, I may have to bring it back with me. So considerations of this sort have to do with availability of your ownership alternative, bicycle, car, motorcycle, and has to do with them being brought back home. So you need to bring your car back to the garage at home or motorcycle back to the garage at home. So that's why you may actually keep them with you. Mobility as a service gets rid of that ownership dimension. So you wouldn't have to care about where do I leave that thing or where do I kind of park that thing. So that's basically the question here. So many of you mentioned that are familiar with discrete choice models, but I brought one slide here from my lecture on travel demand forecasting, which I really like. So the way I look at choice process is that they can actually be on a spectrum. On one side of the spectrum, we have very deterministic choices that are easy to make and easy to predict. On the other side of the spectrum, we may have choices that may not be as easy. They may be multidimensional and they may require a lot of information for people to even make, let alone trying to predict those choices. That side is probabilistic, difficult to make and difficult to predict because there are multitude of features associated with them and features that may be unknown to the modeler or even to the choice maker. So examples, for example, if I offer you a $1 bill or a $2 bill, it's very kind of likely to assume that everybody will go with maximizing the monetary value here. Examples could be shortest path, for example, sometimes, or an auction, for example. Everybody in an auction is trying to minimize, for example, the cost or maximize their profit. But for a choice like this, an apple versus a pear, some people may care about the water content, some people may care about sugar content, some people may care about other nutrition, some people may care about the price. So how do we model the diversity and heterogeneity of these preferences, especially when there is no certain values for these features? I don't know what the sugar content of a basic apple is. And for an apple, for different apples, these values may be different. So predicting these would require a lot of data, and even then would include a lot of error. So we develop choice models that would kind of reduce the choice process into estimation of utility associated with alternatives. And by estimating the utilities, we kind of assume that individuals would choose the alternative that maximizes their utility. Sometimes estimating the utility for a choice like this may actually be very easy. The utility function would include only one variable, would be monetary benefit. Sometimes the utility function may be a little bit more complex. It may include multiple variables, and it may include variables that are uncertain. But we tackle this like in a very standard and a very kind of well-known and well-established models using existing softwares. Sometimes our choices are dynamic. When I make choice A, part of the decision may actually be made, but part of the decision would depend on the outcomes. For example, if I take public transport, in my head, I know, for example, 3 routes may actually take me to my destination from different paths. But in 2 of those, I may need to make a transfer. The other one may actually take me directly to the destination, but I have to walk a little bit longer. So I may make the decision. Out of these 3, I may take 2 of them, whichever come faster. And then out of those 2, when I get to the intermediate destination, I may follow the strategy that is predefined in advance. So see, that's becoming a little bit more complicated. So it's not a choice once made and acted upon. It's a strategy that needs to be optimized. For people making the mobility choices and the mode choices throughout the day, it's something like that, because considerations are complex. And for public transport, path choice is also the same. That's why I put these 2 papers together in this presentation, where I talk about strategy choices and dynamic choices versus simple choices like these. So any questions before I move on to, okay. So a little bit back to those contexts. Remember the 3 different types of reasons that I talked about. So individual-based research, that's usually you will see in papers from social sciences, behavioral sciences, and even from geography experts, versus trip-based models that you would see from transport engineers and transport planners. The individual-based takes into account the individual, the characteristic, how old they are. For example, what's their level of education, their level of income, their habits, their lifestyles, so on and so forth, their attitude towards sustainability, so on and so forth. And they assign people different choices. They predict different choices for individuals, regardless of where are we talking about, which particular trip, what origin and what destination are we talking about. Usually, the trip dimension is missing in this section. Versus, in choice modeling, in transport, especially with the software, majority of software that we use, we know basically what particular origin and destination are we talking about. For example, in four-step travel demand forecasting, we take into account the origin zone, destination zone, quality of travel by different modes. For example, how long does it take to take public transport? How long does it take to drive? How long does it take to walk? So on and so forth. So we close the loop between origin and destination, and we use a specific information. What's missing? The decision before this and the decision after that would affect these decisions. What is missing in the existing literature? What we're proposing here becomes like a network of decisions, like a strategy. In this strategy, we would consider, for example, the first trip from home to work in the morning, and then to shops, and then back home. And then, in terms of options, if I have driving and motorcycle available, they will only be available to me at home. After home, if I choose to take a taxi or public transport or walk, these modes are not going to be available to me. So depending on the first choice of the day, I may be possible to leave my motorcycle and then from work and then take a taxi and then come back with the taxi to my work and pick it up again. But the other way around is not possible. You cannot leave your car at home and walk to work and then from there access your car. You have to walk back home and pick it up. So this is what we're proposing. It's like a path choice because we represent the sequence of modes in a network, and we identify an optimal path for an individual to go from home all the way back home. So that's what we're proposing, and we're using strategies in path choice and techniques in path choice modeling. So the literature of path choice modeling has been very, very challenging over the past 20 years. Many researchers have been dedicating their research to path choice modeling because there are tons of issues with path overlaps and the inaccuracy that path overlaps introduce. My favorite methodology is from Mogens Foskera from Denmark, Technical University of Denmark. He introduced a very interesting method based on dynamic programming and based on dynamic discrete choice. The idea in his method is that when you're at node, at intersection, for example, here, K, then the decision which way you go is usually considering how long this particular link is, how costly this particular link is, how long does it take, and an expectation what's waiting for you when you get there. Because your destination may be somewhere else. So you should have an expectation what's happening at the intermediate destination and how long does it take to get there. So that's the dynamic kind of programming paradigm here. So it's called recursive because the model is estimated in a recursive manner. So you start by modeling the individual's choices, what choices they make at every node along the path. So it's one choice at a time, and it's estimated recursively. So what we use is basically, we use the methodology in recursive logit, and we apply that to mode choices throughout the day. So it's a simple idea, basically. What's really novel here is that, obviously, for every mode, we need to consider, for example, from home to work, if I drive, how long does it gonna take to drive? How much fuel am I going to spend? And do I have a car or not? Do I like? All of that information is considered in this link. But in addition to that, for other modes, I would take into account all the accessibility components and individual components. In addition to all of that, so for all of these trips, we would take into account all of those information. So this is a very intense network that is produced for every choice maker. So for example, if I have 20,000 choices, I would have 20,000 networks like this with variables, values associated on every link. In addition to all of that information, we use a very interesting trick because we want people to bring their cars back home or bring their ownership mode, whichever it is. It may be a car, it may be a motorcycle or a bicycle. We want them to bring it back home because that's what people do. So in order to make that happen, we include a parameter here. We call it a deposit utility. And that deposit utility is paid for every ownership mode that is taken out of the garage. And that deposit is returned to individual in the last link when they bring it back home. So when they bring it back home, the same parameter with the negative sign is assigned here. And this parameter is estimated in the model. 20,000, for example, trips. We look at the path they took, and we model the utility that they perceive from all these links, and we estimate the parameters based on observed data. Does it make sense to you? It's basically a mechanism that we design here, and we throw data at it. We throw data at it to estimate the parameters of that mechanism. So for every mode, we would eventually have, in addition to everything else, for example, the disutility of travel time, the disutility of waiting time for public transport, the disutility of the cost that we pay, so on and so forth, we come up with the disutility of leaving the car out somewhere in the network and not bringing it back home. Sometimes it happens when you go out for a party, for example. You go out and you drive your car, you go to a bar, and then you may get drunk and you may not bring your car back home. You may leave it there. But there's a disutility associated with that. Someone has to go and bring your car back. It may be you, you may have hangover, it may be your wife or your spouse or your so on, a friend. So there's a disutility associated with that. And we want to estimate that disutility too. That disutility may be higher for car, less for bicycle, higher for motorcycle, so on and so forth. So we estimate that as well. The process is a little bit complicated because, again, it's not a single choice. It's not a single data for every individual. For every individual, we have to create a network of decision for that selection of tours, and then we have to solve the parameters and optimize the parameters iteratively in a likelihood maximization kind of model. So it's a maximum likelihood estimation. What it basically does, for those of you who may not be familiar with it, maximum likelihood estimation searches over the entire space of parameter values and comes up with the set of values of the parameters that best explains the observed choices. So it maximizes the probability of observed choices based on the model. So iteratively, we search over the space of our parameters and we maximize the likelihood of the model. And that's how the parameters are produced. So this is basically the set of parameters that we kind of calculate. The paper is under review. It's under revision actually right now, but it hopefully will get published soon. So if you're interested, I can share with you a copy of the paper too. What's interesting to me, for example, is the deposit values. The rest of the coefficient, they all make sense. If you're familiar with choice models, the disutility of time across different modes, they make sense. The parameters are all kind of significant. What's interesting to me is that the deposit value for car is actually very high, is equivalent of 40 minutes. So if you leave your car out somewhere, it is as bad as having another 40 minutes next day dedicated to going back and bringing it back on. For bicycle, it's a lot less. Many people leave their bicycles out. And many people may actually carry the bicycle on public transport. That's something that we neglected in the choice model. So that's why this is less. But for motorcycle, it's actually a lot more expensive because motorcycles are easy to steal. And stealing bikes and motorcycles in Melbourne is a serious thing. I hired a postdoc a few weeks ago. The first week he bought a bicycle for a couple $1,000s. The day after he came to the office and said, oh, my bicycle is stolen. So God, I should have told you, do not lock your bicycle outside, or at least use proper locks. But anyway, they get stolen. So for motorcycle, people do not leave their motorcycles out. They bring the motorcycle all the way back. But the rest of parameters are also interesting. So this is a comparison of a baseline model versus our model, especially for a tour of 5 trips that the individual drove. So our model does predict driving really well. Baseline model estimates that the person may actually take public transport because public transport in the first trip of the day is very efficient. It's fast. They would take public transport. The next trip they would take public transport. And then passenger car is not available for that particular trip. The best alternative that it can predict is car passenger. Someone gives you a ride. Because this was a long trip, it was supposed to be very expensive. It was not supported by public transport. So the best that the model can predict is, okay, the person is better call someone to come give them a ride. That doesn't happen. The person actually drives. The person brings their car from home and they drive the entire day because they cannot rely on a friend to come pick them up. That's the value of mobility as a service. That's where you can actually outsource a set of trips that are difficult to cover by public transport, and you can bring people to use public transport, leave their car at home, but provide this driver role that they need, that mobility that they need as a service. We usually rely on our friends and our family to give us ride for the mobility services that we need. But the idea here is for government to produce that service. Oh, I'm so slow today, running out of time again. So I may have to skim through the second presentation really quickly. This is again another example. True data was actually car driver, and our model does actually predict it well, but the baseline model predicts transit, car passenger, transit, car passenger. That car driver doesn't exist, so the individual drives. That's the difference. So any questions so far? Please, yeah.
So are the activities already established, like for the tour stage?
Yes, so the location of these activities are established, yes. That's an assumption. That's a big assumption. And to be honest, I actually have that in my model caveat. So that was a really good question. So the location where people go and how long do they spend there, all of that we assume is constant. And it's regardless of the mode that they take. In reality, people make decisions that are intertwined. The mode they choose dictates their destination and vice versa. I'm really interested to explore this. I don't have a sponsored project on this, but I'm really interested to develop a model that the destination locations and the mode is made in combination. Good point.
I'm a social scientist. I do not belong in this room.
Great.
But
You do actually. It's actually social scientists deal a lot with choice modeling, right?
we do. And I also do automated vehicle policies, so I'm kind of involved in the literature. But I'm wondering, so when we do choice models, we always include demographic variables. Were they included?
Yes, yes.
And what kind of demographic variables were included?
Very simple ones. We have only gender, age, and if they, senior citizens. So gender and age is the only socio-demographics that we use. But I understand models that you develop in social sciences is usually a lot more intense and more sophisticated with individual characteristics. So that's why it has its own cluster of research. So characteristics of individuals, their attitudes, preferences, what do they care about, where do they come from in terms of class of thoughts and class of values, definitely important. The focus in this particular paper is the hidden anchors associated with destinations in the network. Good point, yep. Okay. So I just jump on this caveat because it was asked. I just talk about the next topic for less than 5 minutes or so, but I just wanted to present this one as well. This was again another paper that was not sponsored, and it took me something about 4 years to complete, because when you're involved in sponsored research, you need to deliver to the sponsor really regularly, and you usually do not have time to do your own research, the research that you love. So I started this research in Brisbane when I was working in University of Queensland, but I completed it when I was at MIT. So it's basically based on Brisbane data. And it's a strategy-based recursive path choice model. I just want to talk a little bit more about assumptions in this model, because that may actually be unique and interesting to you. The model itself and the methodology you can read about in the paper. So path choice strategy is actually a very interesting kind of set of assumptions. In public transport, we usually assume that people travel with the strategies and they try to optimize their strategies. They usually make their mind, which stop do I go to? And from that stop, they have a set of routes. Whichever comes first, they would take that one, and then they adjust their strategies according to the choice that they made, to the route that they boarded. Sometimes the paths may actually physically diverge. They may need to make different transfers, but the strategy may be unique. So what we usually do in many softwares that do simulate passenger path choices is based on optimal strategies. Optimal strategies basically like shortest path, like fastest alternative. You come up with a sequence and a collection of alternatives. Here an example with Brisbane to give you a little bit of context. This is a cultural center in Brisbane, and there was a bridge that would go under the city, and 100 different bus routes use this bridge and serve this station. So I just wanted to look at different strategies. For example, very simple trip from Brisbane South Bank to Indooroopilly. My code produced this strategy as fastest strategy, meaning that there are about like 60 different routes that you can take at this stop. Whichever comes first, just board on that one. Depending on where it takes you, then you would make different decisions. So optimal strategy is given here, but people do not behave like this. They don't know all of these alternatives. They may actually consider a few of them. They may know some of them go the common corridor, but they probably do not know all of this. So it's not realistic. So if you want to predict people's choices, this is not a realistic estimate using optimal strategy. This is just something that the computer can read and can process. So what we tried to do here was to change this, to develop a model based on fare card data. Look at fare card data over an entire year, for example, and then look where people tapped in and tapped out, when did they make the transfer, and we produce, again, a strategic model. A sequential choice, recursive, that decomposes the choice of boarding, alighting, and transfers. So these are 3 different choices. And then we define utilities associated with each one. So utility of boarding route I at the stop A would be represented by BIA. Utility of alighting at every stop would be with A, and utility of walking to different transfer locations would be given as well. So for every utility, we work with log sums, basically. So utility of boarding route I is estimated from the maximum utility that you can get from alighting at downstream stops. Regardless of where you alight, you would get a utility of having access to the downstream stops. And these are connected. So utility of alighting at a certain stop comes from the utility of walking to different alternatives that you can make a transfer. And then utility of walking to different stops comes from the boarding options that are available at those stops. So imagine if you have a model like this for an entire city, that for every route you would consider all the downstream strategies and alternatives, then this is a giant model. We're talking about millions of parameters almost. And we need to make a lot of simplifications. We need to make many of these parameters constant and many of these parameters uniform across different stops. So we estimated this model, and it turned out to, estimation process is again unique because there's no software to estimate this model for you. None of the existing discrete choice models can do this. Again, a mechanism that we throw data at, and we hope to estimate the parameters from data. Then just results. We went all that crazy path. What's interesting is that we get similar results from basic models. But what's really valuable here is that this time, instead of working with optimal strategy, which is the shortest path strategy, we have a realistic model that can be applied to strategies this time. So, for example, I have a scale parameter and I have utility coefficients that take into account minutes of in-vehicle time, minutes of waiting time, minutes of walking time, and these parameters tell me how much people care about optimizing their travel time and how much travel time gets traded with waiting time and gets traded with extra walk. Some people prefer to make less transfers but walk longer distances. Some people hate waiting time. They just get on board every vehicle that comes and then they walk longer distances. And this model can explain almost all of those behaviors on the aggregate level. So big data, value here is if you have a complex process, if you have a complex mechanism, and you throw big data at it, it can be calibrated well. So in terms of conclusions, recursive logit is proving to be very effective for modeling strategic and discrete choices. More important than that, and what's really central to my research is big data. Big data on traffic side, big data on choice modeling, and big data on public transport. I genuinely believe that there is a paradigm shift in transport science from model-heavy research to data-heavy research. And if we can use our methodologies to process the data effectively and bring out insights, we will be successful in transport engineering. And because of that, we need to know big data, we need to be able to process big data, and we need to be able to work with big data and machine learning effectively. So with that, I think we're already over time. Thank you very much for your attention. I hope I didn't bore you.